Hello everyone, today we are gonna discuss some exercises on DFT. So generally speaking, DFT is sampling from the frequency domain. So at the beginning, we only know the DTFT, right? So originally, we have continuous time signal in the time domain, and then we will get also a continuous spectron in the frequency domain. After that, we feel that we have to sample the signal in the time domain. So we sampled in the time domain, and then we get a continuous periodic frequency spectron. And the period is 2 pi. Now, we want to sample it in the frequency domain. And back in the time domain, we get a periodic discrete time signal. And the periodic is n, while the interval in the frequency domain is 2 pi over n. And this is how we develop this concept, all right? And at this step, this is DFT and inverse DFT, of course. All right. So today we'll focus on DFT. So I prepare a question that check your understanding between the DFT and our traditional analog signal. So suppose we have a continuous time signal xa of t, and we know that its bandwidth is 3 kHz. All right. And now we want to use an n-plane DFT to compute the spectron of the signal. And what is our requirement? Okay, we want the resolution to be less than or equal to 50 Hertz. And the resolution we discussed here is basically the separation between the sampling and frequency domain. So we want the resolution to be less than or equal to 50 Hertz. All right. So the unit is Hertz here. But you know, no matter it is in Hertz or in rad per samples, you're supposed to know how to convert them. And here are the questions. Question 1 is, given all these known facts and the requirements, please determine the minimum sampling rate and also the minimum number of required samples, and then the minimum length of the analog signal. And then you have the intuition that the length of your signal is somehow related to your resolution. All right. So let's start with the easiest one, the minimum sampling rate. Any idea? Well,
would it
I guess
relate to the Nyquist rate at all, or no?
You're right. Thank you for unmuting. So the question 1 is basically the Nyquist rate. So the minimum is basically the Nyquist rate and 2 times of the bandwidth. So it is 6,000 samples per second. Thank you. And about the question 2, we need to consider the n, the number of points in DFT. So start from the frequency first, the sampling frequency first. All right, we know that. All right, so we know that if we take n point DFT, we'll have an interval of 2 pi over n, right? But it is in the unit of omega. and but now our resolution is in hertz, right? So we'll have the conversion between the omega and your f. So what should be? And like we discussed in the lecture, so 2 pi over n is for omega, fs over n is for big F, right? So this is hertz, and this is rad per sample. All right. So in this case, we should use fs over n. It stays equal less than 50. All right. So things become clear, and we want to know the minimum n, right? So the n should be bigger, equal to fs over 50, and write them in their place. So the answer is 120 samples. You need to at least apply 120-point DFT to get a resolution less than 50 hertz, less than or equal to 50 hertz. So you'll see that the more points you apply in DFT, the better resolution you get. And let's come to problem C, the minimum length of the analog signal record. So what does it mean by the length of the analog signal? If we go back to the time signal diagram here, we'll see that here the period is n times, right? And we also, if we also know the interval between each samples, we can get the length in the unit of time, which is basically seconds, right? So n, you can say that n, the unit of n is just samples, and we want to know how many seconds does a sample takes, and then we can convert it into the minimum length. So it is basically time. I guess some of you have already figured it out. So we have n samples in the time domain, and we know that we're sampling at fs. So the interval should be ts, which is the inverse of fs. All right. And you notice that it is exactly the inverse of our fs over n. So it should be all right.
Can you explain what it is again? Just like where that comes from?
Sure. So about problem C, right?
Yeah, problem C.
Thank you. So when we want to apply n-point DFT, the time signal is repeating in the period of n, right? So every n samples form a period in the time domain, and the interval here should be ts, which is 1 over fs. All right. So if we expand it, it should be, which is 1 over 50 seconds.
I see that now. Thank you.
Thank you. So yes, so we say it is a minimum length because we can increase the n, right? To reach the resolution, we can make n much bigger, and in this case, the nts will also become much longer. But here, we want to have the minimum number of required samples, which is minimum n, to reach this resolution. And correspondingly, the length of the signal record required will also be its minimum. So that is the logic of this problem. And of course, the signal itself with support, the support length can be smaller than n, but here we are talking about the general case of the signal you require for the general case. So it will apply for any signal with the length of 0.02 seconds.
A quick question.
Sure.
In this part, maybe I missed it, but for part B, when they talk about resolution, why is it fs over n and not 1 over n for the frequency case? Do you know why? Or because I thought maybe I'm misremembering, but I thought because I thought in the DTFT you already scaled by fs. Like, wouldn't fs be at position 1 in the DTFT? So wouldn't it be like, or maybe not?
So in DTFT, we scale the magnitude with fs. So in DTFT, a signal with original with magnitude 1 in spectrum will become a signal with the magnitude of fs in spectrum. So it is a magnitude change in the frequency domain. But here, yeah, they're different.
Or no? I was gonna say, doesn't the axis change as well when you change from continuous, like sampled to like discrete? Like, don't you like divide the axis by fs?
Yes. No? So I guess you're talking about this. So in the frequency domain, when we apply DTFT, we have the range between minus pi to pi, or fs over 2 to negative to positive fs over 2, right? So these are matched. And for DFT, for convenience, we shift it to 0 to 2 pi, and
okay. I guess I get that, but I thought for some reason, like, if you scale DTFT for fs, you'd have 0 to 1 instead of 0 to fs, but maybe not, I guess. Never mind.
It is 0 to 2 pi.
Okay, so we never like try and convert, like, okay, never mind. I think I get it. Thank you.
Great. So I guess you're saying about the small f. The small f is the big F over fs. In this case, you'll get 1.
Okay, I see. Yeah.
And the small omega is 2 pi f.
So okay, in that case then, what's the difference between large f and or why do you have to use large f instead of small f here? Is it because like small f is in terms of like not an actual frequency, it's terms of like it's a ratio, and when you want resolution of 50 hertz, like that's an actual frequency, so you have to use an actual frequency. Is that why you use large f here?
Yes. So the hertz refer to our big F.
Got it. Okay, it makes sense now. Thank you.
You're welcome. Right. Yeah, I know the units, the conversion, the different notation seems very confusing. Okay. So let's come to the second problem. In this problem, you see the relationship between our Fourier transform, of course, the DTFT and the DFT, just as you guys have mentioned. So first, let's start with something we're familiar with. So determine the Fourier transform, or you say DTFT of this signal 1, 2, 3, 2, 1, 0. And let's say it starts at here. So we want to get this. So to save you some time, I'll just do it myself. You can check if it is the same as you think. So the equation is from negative to positive infinity. We times the x of n with e to the j omega n, right? And then because x of n is only non-zero at these indexes, so we can write it in this way. So this is x0, this is -1, this is -2. So we have -2. All right. And please correct me if I'm wrong. And let's substitute the values in. This should be 1, this should be 2, this should be 3, this is 2, 1, and 0 something. Great. So you see that we can combine the e to the j omega and e to the minus j omega. And similar for this two terms. And I'll combine them. Great. So we are done with problem A. And now we want to do this. We want to compute the 6-point DFT. You notice that we have exactly 1, 2, 3, 4, 5, 6 sample in this signal. So theoretically, can the 6-point DFT recover the signal? For convenience, we just write 3, like the start point of the signal, and then it is periodic in a period of 6 in time domain, so we can make a smart change to the x of n. We basically do nothing but shift the 1 and 2 at the end of the sequence, because it is periodic here for DFT, so they are basically the same. Any question about this? All right.
Question: how do you know if there's enough points in the DFT to recover your original signal?
I see. So our conclusion is, as long as the n is bigger or equal to the length of your signal, it can recover fully. So
you're
here
saying
we have 6.
So length is 6 and n is 6 here also, right?
Yes.
Okay.
Yes. So we assume that they can reconstruct pretty well, and later we will check our conclusion. So record what is the equation for the DFT. So one difference is it starts from n from 0 to n minus 1 instead of to infinity, and then the e to the j omega n becomes e to the 2 pi over big N, and then k. All right. So this sum is summing over n, and after some computation, you basically get a function in terms of k. All right, so let's do the calculation. So it starts from 0. So this is basically e to the minus j 2 pi over 6. So it's pi over 3 and k. Now our n is 1, we will get, right? And let's continue doing this. 2k this time. 3k, 4k, 5k. Okay. All right. And as before, we substitute. Oh, sorry, I wrote one more term here. See, I'm a bad example. Don't do that. Check your index. Okay. And then same as before, we can we can merge them and get cosine function.
Sorry, can you show that? I was kind of confused on the last one.
The last
to show
one?
the step. Oh yeah, are you able to show the step for this one? How you convert it into the cosine?
Sure.
Thank you.
So cosine, let's say cosine omega n is equal to half of the sum of the two exponential terms. So you see that, yeah. So this is basically, and plus 2 pi, you get this, right? And you see that it is opposite of the minus j to something, and then you can convert it. Does it answer your question?
Oh, sorry, I was muted. Where did you get those values? You have j 5 pi over 3, and is that for the last one? So v5, u5.
Yes. So these two will form a pair, and then get you a cosine function.
I mean, you just add 2 pi j 2 pi to it, to the other one.
Yeah,
Okay.
you are right. Yeah, so we are making use of the periodicity of our exponential term. And then we'll get 3 plus. Thank you for your question. Great. And now it comes to the most interesting part. Oops. So this is x of omega. This is b of k. Anyone? So let's try. If we make omega equals to pi k over 3, which is 2 pi k over n, it will become 3 plus 2 cosine. And then, anyone want to say something?
You're saying it looks a lot like our DFT almost.
Yes. Yes. So so the v of k is basically one period of the x of omega. We know that the x of omega is periodic, and vk is just one period of it. 3 pi k. Okay. Another thing is I want to so someone asked me on Discord about the conversion of an impulse train in the frequency domain. So I'd like to introduce it a bit here. So suppose we have an impulse train. So it will look something like this. All right. And since it is periodic in time domain, we would like to apply the Fourier series, right? DFS. And we know that for DFS, the parameters A, K describes their properties. So we'd like to compute the AK. So basically, and because within a period, the x of n is only non-zero at the first index, which is 1. So the result will just be 1 over n. All right. And therefore, because we know that the DTFT of an exponential function will be an impulse. So since it is x of n is a series of exponential parts, after the conversion, we will get a sequence of impulses, and this is basically the omega here. So it is the frequency shifting becomes a exponential part in the time domain. So periodic impulse train will still be a periodic impulse train in the other domain. And this basically reveals the intuition that when you sample in one domain, you get periodic result in the other domain. So it is equivalent to say when you sample something in one domain, that means you multiply the time an impulse train to that signal, right? So the sampling basically means you multiply a signal with the train, right? So for example, if the train is called it's called what? It's called S. If it is x of n, our xn is like x of t times the Sn, right? or you can also define it as S of t, where the S of t is only non-zero when t equals to n. They are the same. So the sampling basically means you time something with your impulse train. And the periodic period, or you say periodicity, is basically convolve a signal with impulse train, right? Because the train is a series of impulse, and when you convolve with an impulse, applying the shifting property, it is basically replicating your signal at a different index, right? So if you convolve with this impulse, you're basically shifting your original spectrum to a new place, right? And then you when you're convolve a signal with an impulse train, that means your original spectrum, or you say our original time signal, no matter what domain you are, it will shift to a new place periodically. So the idea behind the concept that sampling produce a periodicity in the other domain basically means that when you multiply a signal with an impulse train in one domain, you convolve a signal with the impulse train in the other domain, and multiplying with the train will result in sampling, and convolution with an impulse train will produce periodicity. So I guess this is inspiring for you. All right. So that's the end of today's discussion, and I'm available for any question.
Yeah, I have a question. If you go back to the problem 2 example, the very end, can you ever explain what you're doing when you plug in the 2 pi over 3k into the x omega equation?
Yeah. So you see that the 3 remains the same, and this term is the same to this term, and then this term is supposed to be the same as this term. Yeah, but
basically what you do would you just plug it into, like,
yes.
I'm confused on what the previous step is supposed to be, like where you show omega goes pi k over 3, like you plug that into x of w?
Yes, x of w.
So, but the thing is,
this is
you have
xw.
Okay. Go ahead. Sorry.
Yeah, I should write it on here.
So you just swap the n and the wait. Oh, I see. Got it.
Yeah. So originally the omega is continuous, right? Continuous in frequency domain. And now you set the interval to be pi over 3, which is 2 pi over 6. You set the interval to be this. And then on every pi over 3, you will take a k. So you get pi over 3, 2 pi over 3, 3 pi over 3. So you're basically sampling the x of omega.
I see.
Yeah. And the k is means how many pi over 3 you get.
Got it. Thank you.
You're welcome.
Is the difference in the equations because we moved the v of n, made it in a different form than x of n?
Oh. So if you observe the x of n and v of n, you'll see that they both start at 3, right? 3 to 1.
I see that. I'm just wondering if maybe that's what made it off, because they're supposed to be equal when we find v of k.
Yes. So if you let alone DFT, so they are different, right? Obviously they are different because the Vn only have non-negative n, and for x of n you even have x of -2, x of -1, right? So observing the signals themselves, they are different. But when you apply DFT in the frequency domain, you are actually repeating the x of n in the time domain. So after repeating, you can take any n period.
Yeah, I get that. I was just wondering
yes.
if like, because the final step, you said that they were supposed to be equal, but they weren't, like at the very end.
Yeah, I guess there is some computation error. So
Where did the cosine 4 omega come from in the first, when you calculated x of omega? Where did the cosine 4 of omega come from?
oh, you're right. So I make a mistake here. So it should be, thank you so much. So this should be omega. All right, so now they're consistent. So you see that 2j omega and minus 2j omega will form the cosine 2 omega, right? And then the j omega into the minus j omega will give us a cosine omega. And then if we follow this equation, and then they will be exactly the same. Woohoo!
Okay, that makes sense. Thank you.
Thank you. I feel much better.
Sorry, one more question about that. So when you have the identity of the cosine omega n equals e to the negative j omega n plus e to the j omega n divided by 2, where does the divided by 2 come into play in this?
What is what?
The identity that you wrote, I think for the next one when I asked, cosine omega n equals the exponentials over 2.
Yes, I use this equation.
Yeah, so where does the divided by 2 come into play for this? Because I understand where you add them together.
Oh. Yeah, you're right. Well, I should go back to primary school and learn it.
So basically,
Division again.
would you divide those by 2, so it'd be 1 times cosine and 2 times cosine?
I think it's still right, because if you multiply what she wrote just now by 2 on both sides, right? You get 2 times.
Okay.
Yeah.
Thank you.
If you multiply by 2?
So
yeah. So,
you can do it. You can.
Like this.
Mm-hmm. Okay. I see. But
Well,
you're just adding them together. Okay, so I guess we could just do that. We add them together, ignore that.
Yeah.
Okay.
So this is 1, this is 1.
Uh-huh.
And they generated 2 here. And this is 2, this is 2. So they generate 4 here.
I see. Right. Thank you.